Hey, AP Physics C students. I was just going through your homework and worksheet 3, number 6, and a lot of you did pretty well on it, but I saw a couple mistakes that were really common, and I just want to address those right now. Okay, so I appreciate you guys starting to use PDFs. I don't know if that's easier on your end, but it's a lot easier on my end. And a couple of you, I actually went through and annotated a couple things on that homework because this is a really important problem to be able to do. This setup with a pulley that's got mass and something hanging off it, the cord wrapped around it. It's a lot like that strange problem I did in the last video that was like the sphere and the mass. Very similar. You really have to know how to do these problems because there's all different kinds of ways to set that problem up. The one with the mass, the pulley, the mass on a table is a similar thing. They'll often do ones where it's a mass on either side with a pulley in the middle. And sometimes the pulley is still massless, but we have to know how to analyze this from Newton's second law. The pulley being in there and having mass is just a minor addition, really, to the Newton's second law problem that's at hand here. So let's actually take a look at number 6. Just a side tangent. I had to load up the one printer with ABS, and man, let me turn the focus lock off for a second. I got the settings dialed in like crazy. So those of you that are in engineering too, it's like printing so clean. I don't know if any of you can appreciate this, but this ABS, I dialed in the settings a bit, and man, it is fire, as you kids would say. I just can't even explain how clean that is. Anyhow, side tangent. Let me focus back on my marker here. I just had to share that because that thing is just I was floored at how good that is printing ABS right now. That's the Ender 5 Pro. But anyhow, back to the problem here. We've got the mass hanging off this pulley. Whatever's the pulley, maybe the pulley's hanging from the ceiling, whatever. The rope is tied around it. You release it, the rope starts to uncoil, the mass falls down. So I'm going to call this the hanging mass. I'm going to call this the pulley. Pulley has some radius, capital R. All right. Please get this in your head. You have to be consistent with your coordinate system. This was the biggest mistake. All right, coordinate system. You must be consistent. We know this is going to accelerate down. I'm going to make that the positive direction. Please just make the direction you know it's going to accelerate in the positive direction. That's going to make your life so much easier. Please stop being stubborn about that. It's not Ft minus mg. Everybody just jumps to doing Ft minus mg like it's some kind of equation on the reference field. Please don't do that. Make down or whatever direction it's accelerating in the positive direction. That makes your life so much easier in the long run. You have to trust me on this. So now we set up Newton's second law for each of these objects. All right. So the pulley, it's got the force of tension right here. It's got an F of G pulling it down. It's got actually some sort of force of support, whatever, holding it up. So these two are balanced. They don't do anything for this problem though, right? The pulley does have those two forces. What matters is this force here that's going to cause it to rotate, right? It's not acting on the center of mass, so it's applying a torque. All right? It's not being applied at the rotational axis. It's applying a torque. The hanging mass has two forces on it. It's got force of tension pulling up. Oh, that force pulling down is the force of tension. And it is the same magnitude. These two forces of tension, this string here goes up tangent, pulls down on the pulley and up on the mass. They're the same force. And the force of gravity on the hanging mass. All right? I know this is going to accelerate down. That's why I draw that little arrow. That's the acceleration. I'm going to make that the positive direction going down. This pulley is going to rotate clockwise. Yes, I know typically clockwise means negative, but that doesn't matter. That really does not matter, okay? This is the direction it's rotating in. I'm going to just say that's the positive direction. All right, and now as long as I'm consistent in how I set up my equations, it doesn't matter what I make positive, negative. It's just that when you make down negative, everybody keeps messing up what you have to do with A. If you make down negative, like a lot of you want to, then you need to make the A's negative as well. Otherwise, Newton's second law equations will fail. So Newton's second law for this one, torque net equals I alpha. Newton's second law for this one, F net equals MA. All right, so torque net equals I alpha. The net torque is simply that force of tension multiplied by the radius of the pulley. It's applied at a distance of r from the center of the pulley. 1/2 mr squared is the moment of inertia for the pulley. And alpha, we've done this a few times now in the videos, is A over r. A over r. And this r is the same as our capital R. Remember, when something's rotating, the tangential acceleration, right, if it's got an alpha, tangential acceleration is equal to the alpha multiplied by whatever, however far you are away from this. Sorry, misspoke. Alpha is, sorry, no. A tangential is equal to alpha times however far you are away from the center. All right? So therefore, when I solve for alpha, I get A over r. It's this. The magnitude of the rotational acceleration is the linear acceleration divided by the radius of the pulley. Over here, F net, I made down positive, so it's mg. This is positive. The tension in this case is negative because I'm saying up is negative, equals ma. So the acceleration is positive. If you say down is negative, then what you would have to do is you could do your old ft minus mg, but then you have to say m times negative a. All right, and over here, it would be negative ft mr squared times negative a. It doesn't matter over here. It does matter over here. But anyhow, down is positive. Just make the direction of acceleration positive. All right. So mg, little mg minus ft equals ma. The r's cancel over here, right? This r cancels one of the squareds. This r and this r cancel. So I get ft. We've done this a couple times now. Is ma, big ma over 2. Plug it in for ft over here. So I can use both Newton's second laws. Mg minus capital Ma over 2. This is just algebra at this point, guys. Don't try to, like, this is, you've done the physics and making your force diagrams and setting up your Newton's second law equations. From this point forward, it's simply algebra. All right, so I'm trying to get the acceleration of the system here. All right, so we go through, do this. This is Ma. I have to solve for A, so mg equals A times little m plus big M over 2. A equals m over little m plus big M over 2 times g. All right? If you plug in the numbers, you get about 1. It's about 1.1 meter per second squared or so. All right, and that's the magnitude of the acceleration. It's down. All right, so yeah, whew. Please just be careful in your coordinate system. You really now need to know how to do these problems like quickly, and you need to know how to just do them stone cold. Newton's second law for torque, Newton's second law for linear motion. Then this is the equation that binds, alpha equals A over R, and then do the algebra. All right. So if I was you and you wanted to practice these for the quiz, You know, we're gonna do the supplemental one tomorrow. I'll make a video on that. Just, you know, make up some other shape, right? Make it a hollow hoop, right? And hang some mass off of it, right? Some sort of hollow hoop. You know, give it a random mass. You make it 1.0 kilograms or something. Make its radius 0.30 meters if you want. Make this mass like 0.10 kilograms, you know? It's always going to be less than acceleration due to gravity. If you get something bigger than acceleration due to gravity, you've done it wrong, right? It can't be bigger than gravity because the force of gravity pulling this mass down also has to get this whole thing rotating, right? If you think of energy, kinetic energy, right? If you release this and you think in terms of kinetic energy, it's not gonna, you know, it's not gonna get up to speed as fast as it would without this, right? Because that force that's pulling this down, this MGH, it's the kinetic energy. There's actually gonna be two components to the kinetic energy. This thing's gonna be turning, that has kinetic energy, and this thing's going down, it has kinetic energy. You're not gonna get as much velocity as quick. All right, so the acceleration's got to be less. The smaller this mass is, though, right? I wish I could go back and show you that, though. If you look at the equation, let me turn off my. Okay, that equation right there, A equals mg over m plus 1/2 big M. Well, if big M, right? Let me show you this. This is kind of cool, actually. Mg. I'm gonna write it on the whiteboard so I don't have to hold this up. All right, so acceleration is little mg, this mass, over little m plus 1/2 big M. Well, as this approaches 0, so as big M approaches 0, A approaches G, right? Because if this becomes 0, then this M would cancel and you get G. So the smaller the mass here, the closer this gets to free fall. The bigger the difference between these two masses, in terms of this one being bigger, the closer the acceleration gets to gravity. So it can never be bigger than gravity. 9.8 meters per second squared. Anyhow, all right, guys, please try to do that number 6 again on your own on scrap paper. I'm going to put one like that on the quiz. Okay? Promise you. I promise you, promise you, promise you. All right? Thanks, guys. Have a good night.